Okay, this is lecture 28, and today we'll continue with what we did last time. In fact, last time we sort of stopped in the middle of something. So what we were discussing last time was 4-point correlation function in 5 to the 4th theory. The Lagrangian was this. And we made two set of arguments in the last lecture and also previously. One, all bubble diagrams cancelled by the denominator, which means if I have phi of x1 to phi of xn, which is equal to this, this is the path integral in the numerator and this is the path integral in the denominator. This only contains bubble diagrams because there are no external legs, there are no fields inserted. This contains some bubble diagrams and some non-bubble diagrams, but in fact the ratio of this is an expansion with no bubble diagrams. Therefore, we can forget about the denominator, just write the Feynman diagrams due to this numerator, but dropping the bubble diagrams. So that was one result. Second was that we can keep only connected diagrams. So bubble diagrams were disconnected, but they are not the only disconnected diagrams. There is another kind of disconnected diagram. So for example, in the 4-point function, we might have a diagram like this. So this is disconnected. And we have a diagram like this, and this is connected. Sometimes some books call it fully connected. And the idea is that through some line or other, any point inside the Feynman diagram should ultimately be connected to at least to all of the external points. So I should be able, if I'm in anywhere deep inside the diagram, let's say I have a very complicated diagram which has, I don't know, all kinds of stuff like that, and eventually I get some external lines. So imagine there are a lot of internal lines, but there should be exactly n external lines. Okay, so wherever I might be deep inside, I can go through a set of lines and reach any of the external points. So that's fully connected. And clearly this is not like that, because for example, if I'm on this point, I can never reach this and this external point. There is an algorithm to keep only connected diagrams, but I don't want to go into it here. I might give it as an exercise, but this is what we can do just by hand, and then the expansion starts to look like this. So this thing will be this diagram plus the next simplest diagram is like this. Now let me look at my notes, because you have to label the external lines in a fixed way and not change it. So it will be annoying if I do it in a way different from the notes. Yeah. So I have used x1, x2, x3, x4. It absolutely doesn't matter how you label it, but you must stick with that labeling till the very end. That's very important. So here it's understood the same labeling for the external points. And then there's also this diagram, and there's also this diagram. And what you can see, now I'll just, instead of, just to save my time, I'll write 1, 2, 3, 4. It stands for x1, x2, x3, x4. And you can see that they are different, in the following sense. You can distinguish them by using some words. So you can explain to somebody which diagram you're talking about by saying, well, there's one sort of loop in the middle of the diagram. 1 and 2 connect to one end, 3 and 4 connect to the another end. Here 1 and 3 connect to one end, 2 and 4 connect to another end. Here 1 and 4 connect to one end and 2 and 3 connect to another end. So they are different in that way. Okay. Of course, the calculation won't be very different, but we have to be very careful because we have to add them. So with our conventions, we have to see that we are using the same conventions for all. But these are three types of diagrams. And then of course, there will be many more, which will have more and more internal lines. And from this, it becomes clear that there are external lines. Those are the ones which start at one of the x's and then stop somewhere and join some other line. That's external. And there are always exactly 4 such external lines in any diagram. All the remaining lines we'll call internal. So as an example, this is an internal line. But for example, this one is an external line. And it should be very easy to see which is which. Sorry if I put the camera in a way which is blocking views, but you're free to also move around. Okay, good. Now last time we looked at this first diagram and we just wrote it using Wick's theorem in position space from the path integral rule. I won't derive that again, but we concluded that the 4-point function, so for that diagram, corresponding to that diagram, the contribution is minus I lambda, then product I equals 1 to 4, d for ki over 2 pi fourth, 1 over ki squared minus m squared. From here on, I'm dropping this I epsilon because it's just a pain to write every time, so it's always there. And sorry, this is an I. And then, so this I derived towards the end of the last lecture, 2 pi fourth, delta 4 of summation of all the momenta of all the ki, and e to the minus I ki dot xi. These are 4 vector dot products. So this was a bit of a tedious calculation, but it just consisted of writing out explicitly 4 propagators in position space to this point y, performing the y integral, and then rearranging things so that it was like this. But the nice thing is, this is the Fourier transform of an expression which I'll get by dropping d for k, 2 pi fourth, the integral, and e to the minus ik dot x. It's all in the definition of Fourier transform. So if I drop all those things, whatever is left is the Fourier transform, and it is minus I lambda into product I equals 1 to 4, I equals this, and then there's a 2 pi fourth delta 4 of summation of these ki. And this has a nice physical interpretation. This thing conserves 4 momentum. This always goes with it. These 2 things we never write. We just never write them, but they are always in our mind. It's like those friends we have far away that we remember them all the time, but we never actually explicitly refer to them. So that's this factor. It's just there. Okay. So this is the operative part, and this we should give a name. So we'll say that this is the Green's function tilde for momentum space k1 up to k4. Of course, it's not the full Green's function or correlation function. G is for Green's function. It's not the full correlation function. It's just the contribution from one Feynman diagram. So it's the order lambda contribution. But it's as simple as writing a propagator for every line and putting this factor in front. And the 4 factorial has cancelled. There was a 4 factorial in the Lagrangian. Now last time I misspoke. Actually, at least in this case, it's very easy to see that all the 4 factorial factors will cancel also in higher order diagrams. And we'll talk about how to count those factors in a few minutes. But first I want to use this exercise as a way to state the rules for any momentum space Feynman diagram. So the rules are that this is always there in the end, and then we have to write a bunch of factors which come from the vertex. So remember, this minus I lambda is associated with that point, because in the end it's not, but it comes from the fact that we expanded the exponential and brought down the coefficient minus I lambda over 4 factorial. And it's worth remembering every piece of this. Why minus? Because the 5/4 term is minus in the Lagrangian. It's from the potential. Why I? Because we have e to the is. And why lambda by 4 factorial? Because that was there in the Lagrangian. Okay. And then by doing all possible contractions, 4 factorial went away and we were left with this. So that takes care of the vertex. And then there's one factor of this for every line. Okay. And we see that momenta are associated with lines. So unlike positions, which are associated with points, momenta are associated with lines. And of course, a line is defined by a pair of points, its endpoints. So in this diagram, the positions are x1, x2, x3, x4, and y, of which y is integrated. But the lines are x1y, x2y, x3y, x4y. So there are 4 lines, and therefore there are 4 such factors. Now, one might ask, why is the delta function of the sum of all the momenta rather than saying that k1 plus k2 is equal to k3 plus k4? Why did we get the sum with all positive signs? That's because in the beginning, we chose the Feynman propagator d of x1 minus y, x2 minus y, x3 minus y, and x4 minus y. It was up to us. Now, the propagator is symmetric in x and y, so we could have chosen d of y minus x1 instead of x1 minus y. But we have to fix one, and depending on that, the direction of our momentum will be fixed. And this is a new sort of subtlety, because with positions there was no associated direction, but with momentum there is a direction. Okay, so we'll see that it really doesn't matter what direction I choose, but once I choose it, I should be careful to stick to that choice. So we'll see how the direction is chosen, and in fact, more commonly we like to choose delta for where k1 plus k2 is equal to k3 plus k4. It's just more intuitive. Good. So with all this set of rules, now we can turn to the evaluation of this diagram. Yes?
Did we choose the inward pointing momenta as
Yes. Yes, this corresponds to inward pointing momenta. But remember, we didn't choose it. We wrote this in position space and this came out. So the original sin was that in position space, when we had this diagram, we wrote df Feynman propagator of x1 minus y. We didn't write df of y minus x1. Okay, because of that, associated to that, we got a particular direction for the momentum. So because we wrote df of x1 minus y, our momentum is defined pointing that way. It's just the convention of Fourier transform. If we did it the other way, the direction of momentum would be defined the other way. Now, one important rule, so this much is for the first diagram, which I've rubbed out, but one rule which follows, and it's derived in the notes, is that there is actually a delta function at every vertex, not just a delta function at the end of between initial and final momenta, but there's one at every vertex. Probably you have done this in QFT1. And that means that I can actually assume when I label the diagram that the momentum conservation is satisfied at every vertex. So this is just a rule. And it's very similar to the way we do electric circuits, where we simply say current into in an electric circuit, a network. We have these points where different lines come in, wires come in, and then of course the total current in has to be equal to the total current out, It's the same thing except that these currents are 4 vectors rather than just some one number. But it's the same kind of idea. That's very convenient. So with that, I'll just make this diagram a little bigger. And now let's see how we can naturally put momenta on it. So we'll just call this K1 and K2. Okay, and this time we'll choose the intuitive definition of K3 and K4, namely that they just point out of the diagram instead of in. So as soon as we do this, we know that there will be a 2 pi to the 4th delta 4 of K1 plus K2 minus K3 minus K4. And this means that we can actually always replace K4 by K1 plus K2 minus K3, but it's pointless to do that. It just makes our expressions longer to write. But in our mind, again, it's always true that any one of them can be replaced in favor of the other 3. And it's up to us, and we do it whenever we need to do it, not necessarily now. So we'll pretend that K4 is sort of independent, but we know all along that it's not. Okay, now what about here? So first of all, again, I'm trying to keep with my notes so that you can do this later on your own. Yeah. So we just choose this arrow to the right, and we give this momentum a name Q, and we don't know what is Q because it's definitely not determined by K1, K2, K3 and K4. Why is it not determined? Because here's a vertex. We only know that the sum of these two is the sum of these two. But then since there are 2 lines here, we can't tell you what is the value of the momentum just by current conservation. And there's no other rule. That's the only rule. So Q is arbitrary. But once we have Q, we can certainly say that this one is K1 plus is Q minus K1 minus K2. Because now at this vertex, the incoming arrows are this, which is Q, and the outgoing arrow is Q. So this is done. And of course, we should worry that it works here also. And here we'll find that if we recall the momentum conserving delta function K1 plus K2 is K3 plus K4, then momentum is conserved here also. So we are done. So we have labeled the diagram. That's step 1. Okay. Now step 2 is to write the factors and integrate over them. So the factors are, what are the factors? So now there are 4 of these, okay, and they are exactly the same factors we already had in the first diagram, and they'll be there in every diagram. Is that clear? Every diagram will have these 4 factors, and the problem is the following. If you look at them, it's I over k squared minus m squared, where k is really the 4 momentum, going to be the 4 momentum of some incoming or outgoing elementary particle. And because this theory has only one type of elementary particle, I just put m for the common value of the mass. Otherwise, there's an mi for each ki. But really, you would argue k squared is equal to m squared, because this 4 momentum squared is exactly the thing which special relativity says is equal to the mass squared of the particle. So what are these factors which are actually of the form 1 upon 0? Why are they even there? Okay, how are we ever going to get a prediction out of this calculation for a physical scattering process, given that the actual scattering process has particles whose k squared is necessarily m squared? If I produce an electron in an accelerator, its 4 momentum squared is always equal to its mass squared. It's not negotiable. So do you know the answer to that?
LSZ, we have those box plus m square operators.
Right. So that's a fancy, yes, that's correct, absolutely. And LSZ was done in QFT1. But that's a fancy way of saying something much simpler, which is that you just drop these, always drop the external leg factors. Okay, when you actually convert from a correlation function to a scattering amplitude. So we always drop the external legs, drop, and there's a better word used in field theory, amputate external legs. to get to S matrix. But there's always, in field theory, there's always a but for everything. Sometimes we like to not drop it. Okay, first let me say that when we do drop it, supposing I had a more complicated diagram which had some interaction here on the external leg, this is called the self energy, then you might ask, are we supposed to only drop that? And the answer is no. We have to in fact drop the whole thing, including all its self-energy corrections. So this amputation is a little bit more formal than I'm indicating. But at the lowest order, this quadratic order or one loop order, it doesn't matter because this diagram isn't there. Well, it is there in principle because, for example, I didn't list, but you should have objected at the same order, there's this diagram. Now this is actually a vertex, so this has got two vertices, so of order lambda squared, and this is there. So I should have kept this, and it's part of my rule 2 strategy to drop. So I'm just going to drop it without any excuse. The reason is that we want to focus our energy on calculating the contribution of this loop because that's the hard thing. Now you have two options then. You can put it back if you didn't like me dropping it, or you can keep it dropped and go to the S matrix and calculate a cross section. Why would we like to sometimes keep it? I'll also tell you, but I'm not going to go into details. Supposing we have a very complicated diagram. Supposing I have a field theory diagram which looks like this. Well, this is enough for this purpose. Okay. So this is a two-loop diagram. I'm not going to be discussing that neither today nor rest of this week. But supposing I wanted to calculate it, I notice that by slicing it here, this part of it is exactly that diagram. And this is a beautiful feature of Feynman diagrams. They are basically recursive, that in any big Feynman diagram, if I slice it anyway, I'll find some other Feynman diagram for some other process or the same process at some other order. It's clear, right, that if I slice it here, these two legs, which are actually internal, become external, and then these are already external, and this is my loop, and it's that diagram. So actually I start to get rules with which I can build more complicated diagrams by multiplying simpler diagrams. But those rules are not going to work if I amputated external legs, because I need an external leg sitting here. So therefore, when we do correlation functions, we don't actually amputate, we simply keep our mind open about the need of amputating or not. We just break the problem into pieces and we focus right now on the difficult piece, which is calculating the amputated part of the 4-point function. It's not that the legs are gone forever. You may need them if you want to do something in higher order. You may not need them. That you can always decide later. And I say all these things because, it's very important in research not to take drastic decisions like I have decided to forget about this factor for rest of my life. Sometimes it may come back because you need it. It all depends on what you want to calculate. Even I showed you that bubble diagrams cancel between numerator and denominator. Well, there are some contexts in field theory where we still need bubble diagrams. It's a funny thing, but there are. So yeah. So it's more of a pragmatic idea here. And now with that, you see that there's not much left to write for this. I have to write minus I lambda by 4 factorial squared. This is what comes down from the action with a half. That takes care of these two vertices. I'm not writing anything for the external legs, so I have to write only two propagators, I over q squared minus m squared times I over q minus k1 minus k2 whole square minus m squared. And I have to multiply by all ways of making this diagram. Otherwise known as the combinatorial factor. Okay. Now let me just for once run through what are all ways of making this diagram, and we'll see that in fact 4 factorials both cancel, but in a somewhat non-trivial way. But the half won't cancel, the half will remain. And there are different books which have different prescriptions on how to predict the whole combination, this as well as this. Okay, you can use those, but actually in real life nobody does this anymore. It's all done by software. And so the purpose of doing it once is just to know how to do it. You know, it's like you have, I don't know, multiplication tables or log tables, but we should know how to multiply if we really needed to. But in practice, if something is complicated enough, we just look it up. So in that spirit, we'll work out the combinatorial factor for this diagram in the way that I find most reliable. And so let's do that right away. Then we'll put this factor in, and finally we'll focus on this part. Now this part clearly has a momentum that has not been determined, and the rule of going from position to momentum space is that every integral, every momentum which is not determined is integrated. It's as simple as that. So there is a d for q, and every integral comes with its 2 pi to the 4th. And also every propagator comes with an I and then this factor. So all these things we should just remember. If you remember, when we went to momentum space, we had integrals over all the momenta, right? Because we Fourier transformed the positions into momenta. In fact, we Fourier transformed each xi minus y into a momentum. So there were actually 6 momenta here. Then 4 of them got dropped when we went to Fourier space. 2 didn't get dropped, but momentum conservation at one of the vertices drops one of them, and that's why we only have one left. But what you can easily convince yourself, and probably you have seen it before, is that for every loop, every closed loop, there is one independent momentum. So one independent momentum for each closed loop. Did I start the video?
Yeah.
I think I spent my whole life panicking. You know, I try to remember if I started it and I can't remember. It's like it's 50-50. I would bet 50% I did, but you people are there. You would remind me, I hope. One independent momentum for each closed loop. Okay. Yes.
There would be another delta function too.
See, there are 2 delta functions, one at this vertex, one at this vertex. One combination of them is the overall momentum conserving delta function, which I've taken out. Therefore, there's only one which is effective.
So that would be the red.
That's the one which makes q minus k1, makes this lower momentum into q minus k1 minus k2.
Oh, so you got, okay, fine.
So this is the whole point. Yeah. In momentum space, we label in such a way that momentum is conserved, and we see after we finish labeling how many undetermined things were there, and we just integrate over those. So it's we are bypassing all those steps. We are basically doing them in our head. Otherwise, we would have called this q1 and this q2. Then we would have had delta k1 plus k2 plus q2 minus q1. Good. So for combinatorics, my way of doing it is the following. So there are 2 y's, y1 and y2. There are 4 positions, x1, x2, x3 and x4. And these y's come under integrations. So there's no meaning to separately y1 or y2. They're just integration variables. They could have any name. But x's have their fixed names which can't be changed. They are determined in advance. Okay. So now what I do is, this is an external leg, so it's going to propagate into the diagram. So I draw a small bit like that, anticipating that it has to join somewhere in the diagram. On the other hand, these are interaction vertices, so each comes by expanding a phi-4th in the Lagrangian, and since phi is to the 4th power, there are 4 little legs coming out of each of these. Now I have to join. So I start always with an external one, and let's say x1, and I say, well, what are its choices? Let me count its choices. Well, to make that diagram, x1 simply has to join either one of these 4 or one of these 4, and all such choices are completely symmetric. There's no difference. So there are 8 choices for x1. So I put a factor of 8. Okay. Now that I've counted 8 choices, I implement any one of them since they are all symmetric. Why are they symmetric? I told you, because it doesn't matter what I call y1 and y2, they are integration variables. Okay. So 8 is done. Now let's look at x2. How many choices does x2 have? Yeah, so this is the problem. It doesn't have 7 choices because we are trying to make that diagram. We have to decide what diagram we are making first. And to make that diagram, it only has 3 choices. Good. And once we have and they are all symmetric, of course. And once we have decided that, we draw it. It's done. Yes.
You said y1, y2 are symmetric because
Yes.
the integration.
Yes.
So why do we still count 8? Why not 4?
No, because it still has 8 places it can join. They are symmetric in the sense that we can call them y1 and y2 or y2 and y1. That makes no difference. What I mean is that diagram doesn't know that this is called y1 and this is called y2. This could have as well been called y2 and this could have been called y1. Okay, but the number of choices of x1 are 8 because it has 8 different legs. That way you could have asked why I count 4 for joining this. It's because it's Wick contraction. So in Wick's theorem, I have to take a field like phi at x1 and join it to another field because I have to break up my. So how many fields do I have now? 1, 2, 3, 4 plus 4 plus 4, 12. And I have to break it into 6 pairwise combinations. And how many ways can I do that? That's what I'm counting. So 8 for the first guy, 3 for the second, because it has to join the same place that x1 joined. Okay, now let's go to x3. It would be a mistake to start from one of the y's and ask what it's doing. We should always ask what the external legs are doing. In a more complicated diagram, it could of course be much worse. But as I told you, from 2 loop onwards, nothing is ever done by hand anymore. For my PhD thesis, I calculated a set of 2 loop diagrams, but they were in a slightly simpler 2-dimensional theory. But it was pretty tedious, but that, as I said, is not really done anymore. Okay, so how many choices does x3 have? 4. Because it has to join to the other y, not that one, in order to make that diagram. Now, how many choices does x4 have? 3. Now, we have 2 here and 2 here. Now, it's easy. Pick any one of them. This, it has 2 choices. So, 2. The other one is determined, and we've got our diagram. Well, interestingly, this number is 4 factorial squared. And yes, it was sort of predicted to happen that way. Last time I was asked whether they cancel and I said no, which was wrong. They do cancel, but well, I don't know. I have an attachment to doing things this way whenever I do it for myself. But books will tell you that you can assume this cancels, but you have to have some symmetry factors and few other rules you have to remember. And for doing this, you don't have to remember anything. That's why I like this way. Okay, but remember we did not cancel the half. Okay. Now that gives us, so now we are in a position to actually do the calculation of interest to us. And that calculation is the sum of 3 diagrams. So let's bring them back. Now I'll go back to momentum space for this. Q this way and Q minus K1 minus K2 here. Then the other diagram is like this. So I have to keep these having the same direction and same labels, the external legs. So this is breaking a lot today. And now I have to figure out how to label the internal lines. And what I'll do is to call this one q in this direction, and this as k1 minus k3 minus q. And you see the difference because k1 and k3 are meeting here, and this is q. This one is k1 minus k3 minus q, and let's check that everything works. This one comes in and this one comes in, so we have k1 plus q coming in. Going out we have k1 minus k3 minus q plus k3, so k1 minus q. Whoops, did I do something? Sorry, this is supposed to be up. Yes. Now this is also wrong. Yeah. Oh. Yeah. Let me try to just do it afresh. Which one should it be?
Minus q plus k3 minus q.
With this pointing up, it should be k3 minus k1, no? Yeah. K3 minus k. I'll correct that. Now I think we are good. K3 minus k1 minus q coming in. Add k1, so we have k3 minus q, and k3 goes out, q also comes in, so they balance. So there are 3 lines coming in which together add up to k3, and 1 line going out for k3. And of course this we don't need to worry about by the momentum conservation, it has to work. And the last diagram, which is like this. So again k1, k2.
Sir,
Yes.
if the outgoing is positive,
Yeah.
then shouldn't it be minus of k3 minus k1 minus, like the entire thing minus and the
This
other-
thing?
Yeah.
See, for an internal line, there's nothing outgoing or incoming. It's just going along the direction of my arrow. It's up to me which way I put this arrow. Either I put the arrow upward as I've done, and this is the momentum, or I put the arrow downward and call this momentum q minus k3 plus k1. Both will work. This is the statement that the amount of momentum flowing in that direction is that. Now, when I look at the vertex, I see that incoming lines are 1, 2, and 3. I have to add them, and then I should get the 4th one, which is outgoing. I can also put all in. It's like currents. The same thing you do with circuits. You label different currents in different segments of the circuit. It's up to you. You can have a current going this way or that way. If you have current of I this way, it's the same as minus I going that way. It's just the same idea. Okay. Now let's see in the last diagram how this works. So this time, again, I want to call this one as Q, and this one I want to label upwards. So it should be, again, I think just K4 minus K1 minus Q. Yes. So let's try. At this vertex, look carefully at this. It has K1 coming in, this coming in, and Q coming in. If I add all of them, I get K4, and K4 is going out. So this is correct. Okay. So these are the 3 diagrams. And all of them will have, so this all ways of making, we calculated it to be 4 factorial squared. So let's collect everything for this. In the end, we have half from here. We have minus I twice and plus I twice. That's a 1. All the 4 factorials are gone, and we have this thing. Now we have 1 over q squared minus m squared and q minus k1 minus k2 squared minus m squared. So this was this diagram. Excuse me? Lambda square. Absolutely. That's not going anywhere. Yes. And so this one, now I can define a quantity. I'll call this entire integral I of k1 plus, I'll call this as I of k1 plus K2. Let's give it a little thought. What are the free things? Q is integrated. This is Q, this is Q. There's one momentum, K1 plus K2. I could have called it P. And then I of P is defined by this integral. Okay. There's also M, but M is a parameter of my theory. Of course, the answer depends on M, but I don't need to write M as an argument because everything in my theory depends on the value of M. So this is that. With that notation, it becomes clear that the sum of these three diagrams is nothing but, okay, now I have to introduce one more important feature. I shouldn't forget the lowest order diagram, whose value was minus I lambda. So maybe I'll drop it at some point, but the idea is that I'm doing perturbation theory to calculate the connected 4-point correlation function. So this has to be added to all these. So therefore, I'll write this as minus I lambda plus lambda squared by 2 I of K1 plus K2 plus I of K1 minus K3 plus I of K1 minus K4. Now you may object that actually it is K3 minus K1, but okay, it is, but in fact, you'll see that I is symmetric under inversion of this momentum. Why? Supposing I flip the sign of K1 plus K2, this becomes plus K1 plus K2. I can change all the components of Q to minus Q, then this will become minus. Then in the square nothing has changed, here nothing has changed, here nothing has changed. Integration limits are minus to plus infinity every component or all 4 components. So nothing has changed. So it's an even function. But so you can call this I of K1 minus K3 or K3 minus K1 as you prefer. The important thing is this is the full answer. Therefore there's one integral we have to evaluate and we know the answer. Okay. Now we can focus on this contribution. This whole thing has a name. We call it minus IM. And it's equal to all this. Or do we call it in my convention we call it IM. M stands for matrix element. It's basically the same as my correlation function. So this is the name of my correlation function after the external legs have been dropped. And only the connected part is kept. These are the two restrictions. No bubbles, no external leg factors, and only connected diagrams. That is IM. So this is phi x1 connected and amputated. So this is the name for it. And the reason to put the I in the definition is of course that so that the leading contribution to M is just minus lambda and then everything else is quantum corrections. Beautiful thing is now finally we are talking about quantum corrections in quantum field theory, and in some way this is the single most important reason to use quantum field theory is that we have a very stable and precise set of rules to calculate quantum corrections to anything. And maybe let me digress before we get into the calculation of this I. Let me digress to say that a lot of physics that is done and which is valid physics but which is done outside the domain of quantum field theory makes unstated assumptions about the accuracy. Okay. For example, I don't know if you were ever taught this, but I've heard a lot of people, even faculty, saying this, that photons do not scatter from each other because they are neutral. So light does not scatter light. Have you heard this statement? Okay, it's not true. Why is it not true, or why is it true? It's true because in leading order, there's no diagram like that where 4 photons come in and meet, because quantum electrodynamics doesn't have a 4-photon vertex. However, there are diagrams analogous to this which have 4 photons, and here's a famous example. This is an electron line, and you know that a photon couples to two electrons, psi bar gamma mu psi a mu, that's the coupling. So there is such a vertex. Put together four of them, each has an E, because that's the strength of electromagnetic interaction. So this is of order E fourth, which is the same order as fine structure constant squared. And this is the leading contribution to photon-photon scattering. It gives me scattering of this photon by this photon equals this photon by this photon. Okay. So anyone who says photons don't scatter from photons is only making a leading order statement, because there is no lower order in E term for that. Okay. And this is the important thing about field theory, that we can really be, not only we know leading terms, we know the subleading terms in principle and very often in practice, and we can calculate them, and we can do so to very high precisions. Okay. So here we are embarking on that for a simplified field theory. Why? It would have been nice to do photon-photon scattering, but when you have those, you have gauge invariance and you have fermions, therefore you have gamma matrices. Okay. Great thing about scalar field theory is no gauge invariance, no gamma matrices. This makes the calculation technically much easier. That's the main reason. And I really want here to emphasize the concepts behind it. So we want all the technical annoying things like contracting indices and all to be out of our way. That's why we are doing this example. Good. So now we come to our job, which we have postponed for a long time. And we find that, okay, so I of p is the name of everything other than lambda squared by 2. So it's integral d for q over 2 pi to the fourth 1 over q squared minus m squared q minus p or plus p, it doesn't matter, minus m squared. That's I of p. Okay, remember p is a four momentum. At the same time, if you look at this thing, you realize that after I finish integrating over q, this whole thing is Lorentz invariant, because it only depends on squares of four momenta. Now you may argue that in this term there is implicitly a q dot p term. So the integrand is not dependent only on p squared. It depends on q squared, p squared and q dot p. But after I finish doing this integral, it can only depend on p squared. It can't depend on individual components of p. So actually this is a function of p squared and m squared, and just two variables, and our job is to find that function. Now we realize the following. Supposing I scale each component of q mu by a factor lambda. Okay, now let's put back the integration range. It's four integrals, 1 over q0, q1, q2, q3, each one from minus to plus infinity. Now if I scale q mu to lambda q mu, then the numerator goes like lambda to the fourth, because d for q. The denominator also for large lambda goes like lambda to the fourth, because there are two powers here, two powers here. This in any integral is a diagnostic which tells me whether the integral converges or not. And this tells me that numerator and denominator scale the same way, and this is a sure sign of a logarithmic divergence. Of course, we'll see the logarithmic divergence come out when we evaluate it, but we know in advance that it's going to be there. Okay, so let's anyway press on and see what we can do with this integral.
So how do you see the divergence of this?
Just the fact that the number of powers of my integration variable, okay, so you know that dx by x is logarithmic.
Sorry, I did not see that. The limits are infinite, so
Yeah. So it's just the fact that dx by x is logarithmic, and the way to find that out in this case is just to do it. But in a multivariable case, since we can't just do it and look at the answer, actually we are going to do it soon, is just to estimate the divergence by saying that how does the numerator and denominator scale. If this power was at least a little bit higher than that, we would have a convergent integral. If this was higher than that, we would have a divergent integral, and when both powers are exactly equal, it's still divergent, but it's logarithmically divergent, which is the minimum level of divergence that any integral can have. Okay, good. Okay, so now there's a very nice trick which is very standard. Supposing I have two numbers a and b, I can rewrite 1 over a times b as an integral over a variable x just going from 0 to 1 of a plus b minus a x, the whole squared. So this is called the denominator trick or something. Basically what it does is it takes two different denominators a and b and combines them into the square of a single denominator, but the price you pay is there's a new variable x that you are supposed to integrate. Okay, now I won't insult your intelligence by deriving this for you. It's a very easy integral to do. If you do this integral, you will simply get 1 over ab. It's just an integral from 0 to 1 of a simple variable, and there's no problem with the integral at all. So it's convenient to use, and if we use it on I of p, we find that I of p becomes, of course, there's the integral 0 to 1 dx, and our trick will be to do it last. Then integral d for q was always there, 2 pi to the 4th, and now it is 1 over a, which is q squared minus m squared, plus b minus a, that is this minus this. So q squared cancels, m squared also cancels, and we only have 2q dot p and p squared. So it is, and there's an x, so x times p minus q squared minus q squared, and then the whole thing is squared. Okay, let's simplify it. So now I'm going to collect terms. So maybe let's just do it by hand. Q squared minus m squared plus x into, and in here I have p squared minus 2 p dot q. So remember, m dropped out from this because I had to subtract this from that. So m just dropped out, and it's just p squared minus p dot q, I believe. And now the whole thing squared.
Shouldn't that be m squared, p minus q squared minus m squared?
Sorry? Yeah.
Squared minus m squared.
Yeah, but it was p minus q squared minus m squared also. Both had m squared. This is b minus a. This is b. This is a. If I subtract a from b, the m squared part cancels. Also the q squared part cancels. And I'm left with only p squared and 2p dot q. Good. Now, we do a little manipulation here. And to do this, we basically, so first we complete the square. So here we have q squared, and here we have minus 2p dot qx. So it's convenient to complete the square by writing q minus xp whole squared. Then I have to remove the extra x squared p squared, and then I have to write minus m squared, this one, and finally xp squared, which is this one. I just completed the square between q squared and x 2p dot q, And because that gave me an extra term, I cancelled it, and then these are the two terms which are already there. I just wrote them. It's all in the notes. I'll end in 2 minutes. Now, I will change variables. Q goes to Q plus XP. Now, any mathematician and actually any serious physicist also will tell you that you can't just change variables in a divergent integral because the integral is ill-defined, it's divergent. And if you change variables and then do something, it may not be the same as doing something and then changing variables. Okay. So instead, however, we are going to take the view that we'll be putting some limit on this by hand, which is called a cutoff, to make the integral finite. Then we can change variables freely, but now the limits also variable will change. But we are eventually going to take that limit back to infinity. So with this circular set of statements, I'm going to change variables. And when we finish whatever we have to do, which will be tomorrow, you can question whether it was okay or not. And finally, it turns out that these have to do with taking certain non-commuting limits. Basically, we regularize the theory by cutting off high momentum modes. We change variables, and then eventually we do something very clever to take away the regularization. So I'll do all that. So for now, you may let me do this. If I do this, then this turns into integral 0 to 1 dx, integral d for q. And here I get now q squared, because this has just become q squared. And this quantity, I'll just call it capital delta squared and whole squared, where delta is just m squared minus p squared into x1 minus x subscript. Is that clear? Once I shift variables, then this is q squared, and there's no other q dependence. As far as the q integral is concerned, this is all a constant, which I give a name delta squared. So delta squared is that. Is that what I have? No, I call this, sorry, this is delta. It's not delta, it's called delta. So it's q squared minus delta, the whole squared, and delta is that. Delta is dimension of mass squared. Okay. Now we see two things. First of all, now we clearly see the divergence. It's less messy. There are no dot products of q anymore. We also see that there will be a pole when q squared is equal to delta. And this will turn out to be a problem due to the Minkowski signature, because this is q0 squared, q1 squared, q2 squared, q3 squared. They contribute with opposite signs. So in my conventions, q squared is equal to q0 squared minus q3 vector squared. So the next step, which we'll do tomorrow, is to rotate this contour so that q0 becomes imaginary, in which case this will turn into minus Euclidean q squared, and now it's q squared plus delta whole squared, and there's no pole. Note, by the way, that okay, that's still not true, because delta, we haven't said that it's positive, but we'll come back to that. It will still be easier to have plus delta instead of minus delta. And then finally, we'll try to see how to regularize the integral and evaluate it. Okay? This is all very tedious, and I've tried to make it as simple as it possibly can be made, but it's essential in field theory because generic processes have this divergence that we just saw here, and the divergence comes from very large values of the internal circulating momentum. So it's called a UV divergence. Ultraviolet comes from very high momentum. In position space, you can imagine that it comes from the region where this y1 and y2, remember we integrated? Well, they could be very close, right? We integrate each one from over all of space. There could be some point where they come very close. Now in field theory, bringing 2 points very close is a real problem, because field theory lives in a continuous space, And as you know, for example, the delta function, which identifies one point with another point, delta of x minus y, okay, it's infinite when x is equal to y. It's not just equal to 1, it's infinite. This is the kind of infinity we are getting. These are all due to the continuous nature of space-time and the short distance. So we have to get used to it, and we have to find a physics way to get around it, which we'll do over the next 2 lectures. Yes?
I don't see why using the Minkowski metric would be the problem. Can you repeat that?
No, it's just convenient not to use it. Why you don't see why it would be a problem?
Yeah.
Oh, it would be a problem because with this signature, so you have q0 squared minus q squared minus delta. So whenever q0 is equal to q squared plus delta, we'll have a pole. Okay. On the other hand, if I do this rotation, which I'll do tomorrow, then this will be q Euclidean vector squared plus delta whole squared. And if whenever delta is positive, I'm sure that I have no pole. So I can do everything in the region where delta is positive. Delta is up to me, because delta is a function of p, which is an external momentum, which is either k1 plus k2, k1 minus k3, or k1 minus k4. So I can choose those momenta to at least let me do the integral in peace, and then see whether I can continue beyond that integration region. That's the philosophy.